Now that we understand how to build a neural network using TensorFlow and Keras, we can now do the fun part, which is learning how to build different neural networks for different use cases. So the first one that I'll be teaching you about is binary classification. Before we continue, I just want to give credit to this book here for all the code samples, Deep Learning with Python 2nd edition. That is what I'm using to help teach you guys a lot of these concepts. Binary classification means that if you have, for example, an image, you can classify the image as either a dog or a cat. Friendly or not friendly. It's just something or something else, okay? That's why it's called binary, because there's only two options. Now, you may have heard of the website IMDB. I don't know what that stands for exactly, but it's basically a website that you can, look at movie reviews. And to that idea, there's also a data set called the IMDB Dataset, and it's a large data set of a bunch of movie reviews that are classified as either positive or negative. It's the sentiment analysis of the review itself. So basically, each sample is a bunch of text, which is the actual review itself, and the target that we're trying to predict is a binary class label, which is either positive sentiment or negative sentiment. What's nice about TensorFlow and Keras is that it's actually provided as one of the built-in datasets, so we can import it really, really easily. So from TensorFlow Keras.datasets import IMDB. There's also a bunch of other ones available. Let me just connect to the runtime real quick. All right, so now if I do control space, it should give me suggestions. All right, here they are. So we have IMDb, we have Reuters, MNIST, Sci-Far, Fashion MNIST, Boston Housing, California Housing, which we've already looked at previously. Yeah, so let's just bring in the IMDb dataset, and we can go ahead and import this dataset by doing train data and then train labels. And then we can also do test data, test labels. And now we could do is equal to imdb.load data. And to this, we're going to specify the number of words, which I'll explain in just a moment. So 10,000. So that will bring in the entire data set split into already for us a training set and a test set, which is great. Let's go ahead and just get an idea of what the size of this data set is. So we'll print out train data dot, shape. And then we'll also do the same thing for the test data. So test data.shape. So what this is doing is automatically downloading the dataset, importing it, and putting it into these variables for us, and now we're just printing out the shape. So you can see that for the training set and the test set, we have 25,000 instances each, which is a lot of data. So this should be pretty good for us to train a neural network on, because neural networks love lots of data. Let's now take a look at what a single entry or sample or instance looks like. And here we go, it's a bunch of numbers as a vector. So you can see that it's basically just a list of numbers. So when we loaded in this data set, we also specified this number of words parameter and set it to 10,000. And what this means is that we're only keeping the top 10,000 most frequently used words in our reviews that we have here, okay? The reason we're limiting it to only the most common 10,000 words is because if we don't limit it, we're going to have a data set with huge amounts of data. There's about 88,000 unique words in all these reviews. So if we include all of those in every single sample, then it could get very messy. So we want to make sure that we have it more manageable, and we're going to do that by only including the 10,000 most commonly used words, okay? And that may remove a lot of different words that are more rarely used, but we still maintain a lot of the meaning of the dataset, even when those words are missing, because we still have the most commonly used words, which is more useful, right? We want to have words that are commonly used in different samples across our dataset, and therefore the model can see those words used across those different samples and learn if it's a positive sentiment or a negative sentiment, okay? So anyways, just to keep it short, the number of words parameter allows us to load in only the most commonly used 10,000 words, which also limits the size of our data, which is great. So what this will do is basically when it loads in the data set, we'll also load in a dictionary that is ordered in terms of how often the word is used. So the first element in the dictionary would be the most commonly used word. The second would be the second most commonly used word, and so on, okay? So that is why when we print out a single sample here, we can see that it's just a bunch of numbers. Because even though this is one review that we have here, all of the words have been converted to the indexes of the dictionary for our words that we have tracked, okay? So it's already been tokenized for us, so that's more useful for what we're trying to do, which is, machine learning, right? So to make this make a little bit more sense, we can actually use this piece of code here to translate a single training sample back into actual words using that dictionary I told you about. So we can do imdb.getWordIndex, and this is the dictionary that holds the translation between these numbers here and the actual words that they represent. So if we go ahead and run this one here, this will convert the first sample of our training data into the words. So it says, this film was just brilliant, casting, location, scenery, story, direction. Everyone's really suited the part they play. and you could just imagine being there. You can see that there's obviously some words missing in this that will make it make a little bit more sense, but for the most part, it still maintains its meaning. So hopefully that makes sense, and that's why whenever you print out a single instance of our training set, you only see numbers and not actual words, because each of the words have been translated into indexes that correspond to the most commonly used words that we're tracking, okay? So that's that. We can also go ahead and print out the train label for the first one as well. So train label 0. Let's run this again. So we get 1, and this means that it's positive. It's a positive sentiment, and that kind of makes sense because it's saying it's a brilliant casting, location, scenery, and all that stuff. So 1 corresponds to positive sentiment, and then 0 would correspond to negative sentiment, okay? So we're just trying to build a neural network that can determine if a particular review is positive or negative, 0 or 1, 1 or 0. Okay, so the next step is we need to take our training data and do a little bit more processing to get it ready to feed into our neural network. Because the thing is, it's already numbers, which is great. Neural networks love numbers. That's awesome. But our neural network also expects inputs that have a consistent size. So what I mean by that is every single review that we have in our training set and our test set, they all have different sizes, right? Like different reviews are going to have different amounts of words and stuff like that. One review can be more wordy than another review. So we need to figure out a way to make every single sample of our training set and test set the same size. And that's called vectorizing it, because we're trying to convert it to a vector of the same size for every single sample. And there's 2 different ways you could achieve this. So number 1 is you could pad it. I'm going to show you this visualization real quick, which I think will help your understanding of padding in multi-hot encoding. So padding is actually very simple. So here we got some vectors, vector 1, vector 2, and vector 3. The way it works is basically we find our largest vector. So in this case, we have vector 2, which has 5 elements within it. And we're going to set this as the size for all of our other vectors. Because again, the whole goal of doing this, of vectorizing our vectors to prepare them for a neural network, is to make sure that they're all the same size, right? So if we get the size of the largest vector, we can make sure that they all match that size. And the way that we're going to do that is by filling in the smaller ones with zeros. That's why it's called padding, because you're padding the empty space with zeros. So for example, on vector 1, we only have 3 elements. So we just have those 3 elements plus any zeros to get us to 5 in size. So that's how that looks. And then vector 2 is just the same because it's already 5. That's our largest one. And then vector 3 only has 1 element. So it just has that 1 element plus 4 zeros on the end of it. So that's how padding works. And then we also have multi-hot encoding, which is a little different. So we already have a dictionary of values, right? Which represents the most frequently used words in our reviews that we're making a model for, right? So let's just pretend that we have a dictionary of only 3 words: dog, cat, and bird. And they're ordered in terms of frequent use. So dog would be the most frequently used word. So it would have index 0, cat would be 1, bird would be 2. So this dictionary has a size of 3. So this means that what we're going to do is make all of our vectors size 3. So back in our actual code, we have a dictionary of size 10,000, the most commonly used 10,000 words. So that means that every single vector of our data set is going to be 10,000 in size, which is very large. And now the way it works is for each of the vectors that we have, each index will correspond to our dictionary mappings. So let me give you an example because I think that will help you understand a little bit better. So if we have just a movie review and it just has the word dog, for example, we know that dog is index 0. So index 0 would be 1, indicating that it's present in our review. So we'd get 1, 0, 0. And then let's say that we have another review that has the words cat and bird. So cat and bird, our index is 1 and 2 in our dictionary. So in our actual vector, it would be 0 because dog is not present, cat is present, and bird is present. And then we have dog, cat, birds. So those are all the words in our dictionary. So this would be 1, 1, 1. So basically our vectors just become a thing that represents which words are present. So a 1 in a specific index means that that word is present, and that maps to our dictionary. And then a 0 means that that word is obviously not present in our review. Now, there's different trade-offs, of course, between these 2 approaches. Multi-hot encoding is considered sometimes an easier approach, even though I find padding to be more understandable. But in terms of pros and cons, one of the cons is that for multi-hot encoding, obviously, since we're just marking it as a 1 or a 0 for each of the indexes, we lose track of how many times these words appear in the review. So if dog appears multiple times, if it's like dog, 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 there would only be a 1. There wouldn't be a 3 in the first index. And also the order no longer matters. Previously with padding, we still maintain the order of our reviews in terms of like when the words are used. So we get 1, 2, 3. We don't really change that. But for multi-hot encoding, it's ordered based on the dictionary ordering. So it's ordered in terms of which words are most frequently used. So we lose a lot of the semantic meaning when we do multi-hot encoding like this, meaning that we lose a lot of context on which order the words are used, how often the words are used, and depending on what you're doing, if you're doing something like natural language processing, which is a more advanced topic, this may not be the right approach for you. But this is what we're going to go with just so that we can get started. But I think you just knowing the different options that you have is very important. So you can do padding if you want to, you can figure that out. But today I'll be showing you guys how to do multi-hot encoding, okay? This function here is actually going to do the multi-hot encoding for us. So we just pass in a data set. That's what sequences represents. And this will transform it so that every single instance of our data set has a length of 10,000. So it's a vector of length 10,000. And then for every single element of that 10,000 vector, we're going to put a 1 if that number is present in our original sequence. We're not doing just 1 as a whole number, we're doing 1 dot, which is just a shorthand way of doing like 1.0, which will just make sure that it's a floating point data type. Because neural networks like to work with floating point data rather than, integer data, okay? So to actually use this function now, we can do xtrain. So for xtraining data, we can do vectorize sequences and then pass in our train data that we had above. We can also do that for our test data. So xtest is equal to vectorize sequences test data like that. And we could print out the first one just to get an example here, make sure it works. Here we go. So now we have a NumPy array that represents a vector, which is just the first instance of our training data. And we could see a 1 for every single number or word that appears in our review. Okay. We can also prove that the shape is now 25,000 by 10,000. There we go. So 25,000 instances. And then each of those instances has 10,000 elements within it. Now we also have our labels up here. We have our training data, but we also have our training labels and test labels, which currently are just normal Python lists. So we want to transform those into NumPy arrays and also transform them into floating point data types as well, because again, neural networks like to work with floating point data. So we'll do yTrain is equal to numpy.asArray, pass in train labels like that, and then do as type float 32, which is just basically the default floating point data type. And then we'll do yTest is equal to, and we'll do the same thing. There we go. So now we can just print out one instance. We'll do the first one. And boom, so we just get 1.0. Okay, so that's it for the boring part, which is pre-processing our data just to make sure that it's able to be fed through a neural network and used properly. Now we can do the fun part, which is actually building the architecture of our neural network and actually using it and fitting it onto our data. First things first, let's import Keras or Keras, however the hell you say it. I still don't know. And now we can do model is equal to keras.sequential. And now first we can specify the input shape, our input layer. So keras.input, and now we can do shape is equal to, and now we could do xtrain.shape and get the second one for the amount of columns that we have, and then a comma. So again, what this will do is define the shape of the input that we're going to be passing into this neural network when we feed it in. And so this will be based on the size of the number of columns that we have per instance, per sample, which will be 10,000. Because again, each of the instances in our training set have 10,000 elements within it. Okie dokie, so that's our input layer. So now we can define some hidden layers. So keras.layers.dense. And we can go ahead and do something like, 16 units, which is going to be the number of neurons that we have in this layer, as well as the size of the output dimension. And now we also want to specify the activation. So the activation is going to be ReLU, which we're just going to add another hidden layer on top of that. Also 16 units, also using a ReLU activation. And then now we'll have our output layer, so keras.layers.dense. And we want 1 unit. And then now we're going to have an activation of, instead of ReLU, we're going to do sigmoid. So the sigmoid is new. This is an activation function that used to be used a lot more before ReLU, but now specifically we're using it on our output layer because we're doing a specific problem, which is binary classification. So what the sigmoid will do, the sigmoid will squash the values into the range of 0 to 1 inclusive, okay? And basically it represents the probability of the target being 1 or positive, okay? So basically it takes whatever output we had from our previous hidden layer and squashes it so that every single sample that we pass through this has just one output, one number that represents the probability that that number is 1 or positive in this case. Because again, 1 is positive, 0 is negative sentiment. So basically you want to use sigmoid whenever you're doing something like binary classification because it's commonly used with probabilities, okay? We're going to learn about different activations that we're going to put on our last output layer for different tasks that we do. So now that we've defined the architecture of our neural network, which is a sequential network that has an input shape of 10,000 based upon the second dimension of our input training set, and then we have our hidden layer, which is 16 units or 16 neurons with an activation of ReLU, And then we have another hidden layer with another 16 units in activation of ReLU. So ideally, the first layer will learn some stuff about the data as best as it can. The second layer will try and build upon that and learn it even better to try and learn any complex relationships between the data and the target that we're trying to predict. And then finally, we have our output layer here, which is just a unit of one neuron that has an activation of sigmoid, which again, like I told you, is popular for binary classification, okay? So once we have that, now we can go to compile our model. So model.compile. So compiling again is for specifying the optimizer, the loss function, and also the metrics that we'll measure during the training process. So the optimizer will do Atom again. You can do other options like RMS prop or SGD for stochastic gradient descent, but Atom is a very popular one and widely used one that gives good results. And then we can do our loss function. So before we did MSE, the mean squared error, which is good for regression problems. And I think it's also commonly used with binary classification, but even more commonly used is something called binary cross entropy. This will still measure the loss, which is the measure of how far off our predictions are from the actual values that we're trying to predict. But this one is more suited towards what we're trying to do, which is probabilities for binary classification. So different loss functions have different uses, of course, different use cases. And then finally, we'll add our metrics. So you can add multiple if you want to, but just for now, we'll focus on the accuracy. And all the accuracy is the number of correct predictions divided by the total number of predictions as a percentage. So the loss is what we're trying to minimize, and then the metric is another indicator of how good the model is doing, okay? Now it's time to actually train the model. We can do that by doing history is equal to model.fit, and then we want to pass in our training data, so xtrain, and then we also have our ytrain, and then we can also specify the number of epochs, so epochs is equal to, and we can just do any number like, I don't know, 10 or 20. Let's just start with 10, see what that looks like. And then we could set a batch size, which I told you before is the amount of elements in a single batch. And then your training set that you pass in is going to be split into batches, with each batch being that size. So we're going to do a batch size of 512. This is just an arbitrary number from the example I'm using, but we'll see that changing this number gives you different results. The model will train and converge much faster, which we'll see in just a second, so don't worry too much about that. And then after that, you want to set the validation split, which we'll do as 0.2. So 20% of our training data that we pass in will be set aside for validation testing. All right, and that's it. So now we can go ahead and run this. So just like before, we can see that during training, we get our metrics that we tell it to track. So we get our accuracy for training, we get our validation accuracy as well. We get our loss, which is based on the binary cross entropy, as well as the validation loss. And we can see that over time, the accuracy increases, which is great. We want the accuracy to increase, and the loss also goes down, which is great as well. But of course, just like always, it's better if we can visualize this so we can get an idea of what's actually happening. So we're going to do history. Dict is equal to history.history. And then we can go ahead and print out the new keys for our history. So we can do history dict.keys. Let's run this, and we can see that we now have access to the accuracy, the loss, the validation accuracy, and validation loss, which is slightly different from last time because we were measuring different things. Before we still had a loss, but now we have accuracy instead of MSE, mean squared error, so that makes sense. So now what we want to do is actually plot this so we can visualize it. And then now I'm just going to copy and paste this code, which will access our dictionary and pull out the necessary data, so the loss and validation loss, and also the accuracy and validation accuracy. So let's run this and see what we get. All right, here we go. So here's our training and validation loss. We can see that the dotted line is going to be representing our training loss over time. You can see that over time it goes down. At the beginning, it goes down quite rapidly, and then it starts to gradually go down a little bit more slowly, but it does keep going down, which makes sense because we're trying to minimize the loss on the training set, which will naturally make the training loss go down over time if things are implemented correctly. But for the validation loss, it's a little bit different. So you can see that it starts off, fairly high, I guess, but then it starts to go down, which is a great sign. We want our validation loss to go down. But then you can see that it sort of plateaus and starts to go back up. And this is what I talked about before. This is a sign of overfitting. Basically, the model when training will learn as much as it can, and then it will converge, meaning that it reaches the optimal learning point. And what that means is that the model has been able to generalize as much as it can at this point, and then from there it'll start to overfit, meaning that it does better on the training data versus on the validation data. So that changing direction is a clear sign of overfitting, but if we go down to the training and validation accuracy, you can see a little bit of a different picture because we're measuring something different. We have our training accuracy as the dots, so you can see that that goes up pretty rapidly and then starts to go down or keep going up at a slower rate, but it still goes up to almost 1, which is really, really good. I believe if we check our logs here, we can see that the accuracy is 0.9946, which is a really, really good accuracy, right? But we only care about the model on unseen data. That's the whole point of making a model. So although it's great that our training accuracy is increasing, we also want to pay more close attention to our validation accuracy, because that's the representation of how the model will perform on that unseen data. So we can see that. So we can see that at the point in which the model generalizes the best it can and starts to overfit, which is about epoch 2, I would say. We can also see that the validation accuracy is the highest point that it's able to be, which is almost not quite there, but almost 90%. So that's a really good result if you ask me. One of the most basic things that you can do to fight this overfitting and get the model at the point in which it's most useful is retrain the model, but chop it off at epoch number 2, because we can clearly see that the model converges at epoch 2. So that's the version of the model that we want. So all we got to do is go back up here and change the epochs to 2, and then let's go ahead and run this again. Now, for this particular problem, the number of epochs is really, really low, which is not always going to be the case. Usually you might want the model to run a lot longer, but this model is clearly able to generalize quite rapidly. So that's why having these plots is a great thing. So anyways, it's done training, so we can go ahead and print out the plots again. So now we can see that at epoch 2, we cut it off right away, and our validation loss is just under 30%. And then at epoch 2 for the training accuracy and validation accuracy, we can see it's almost at 90%. So by chopping it off at that epoch, we have fought overfitting because we are not allowing it to continue and overfit. So once you have trained your model and you've chosen some hyperparameters that you feel good about, like your epoch and batch size and all that stuff, what you can do is finally have your model test on the test data, right? That's the final evaluation of your model. So we can do results is equal to model.evaluate, evaluate, and we can pass in our x test as well as our y test. And let's take a look at what that looks like. Well, let's print it out. So results. All right, so there we go. We get an accuracy of 0.885 and then a loss of 0.28. So these numbers here should be familiar to you because these sort of match the last recorded validation accuracy and validation loss that we recorded during training. Of course, they're not going to be the same just because the validation set and the test set are not exactly the same, but they are both unseen data, just at different points in the process. So they should be similar numbers, I would say. And that's it. So that's how you can train a basic neural network to classify the IMDB sentiment analysis dataset. So we're able to now classify individual IMDb reviews as positive or negative sentiment, which is really cool. So we can take what we learned in this episode and really expand this to all different types of problems, which we'll be doing. But just getting this practice of making these neural networks and setting up the architecture, compiling it with the right loss function metrics and all that stuff, and understanding how to read the results and see when overfitting happens, that all of that all combined together is very good to understand, because those are the major parts of building neural networks and what we need to actually know to get a good foundation. Okay, before we end here, I just want to show you guys what happens when you change some of these values here and change the architecture of the neural network, so we can see how the neural network changes. The results change. So if we change our epochs back to, let's just say 10. Let me go ahead and run this again. Okay, so here's the plot that we had before. Let's see what happens when we change the batch size, for example. Let's change it from, like, I don't know, 512 to, let's just do a number like, a common number would be like 128 maybe. They're usually multiples of 2. So let's try that out. All right, so here's our results now. We can see that now it doesn't really have this point where it goes down and then goes back up. It seems to immediately start to overfit right away. You can also see that the validation accuracy starts to go down right away as well. So what this means is that your model essentially during training converges right away, meaning it reaches that optimal point of generalization. So it's going to continue to get better on the training data, but it's basically done all it can with the validation data because it's just continuing to go up right away. So you'll see that when you're configuring your neural networks, these different options here, for example, like the batch size, will have different effects on the training process. So just the batch size itself. So when your batch size is larger, for example, we had it as 512, the model gets a more accurate estimate of the gradient for each of the updates to the model weights. So this will lead to smoother and potentially more stable training, and also give it more time to potentially, learn and generalize based on the training set. But it also could take longer because if the batch sizes are larger, it has more data to process essentially per batch. A smaller batch size, like for example 128 or even 64, for example, can lead to faster convergence at first, but it may also overfit right away, like we're seeing, because it's making more frequent updates based on smaller, potentially noisier samples. So basically, a larger batch size slows down training, but each update is more reliable, which might prevent the model from overfitting as quickly. But a smaller batch size could get you to that generalization point much more quickly, which you may want to save time, but it could overfit really quickly, as you're seeing as well. So it's really important that you kind of strike a balance. In this case, it's already really fast, so a batch size of 512 doesn't really hurt us. So we can essentially give the model more time to generalize and learn on that training data, to be able to work also on the validation data very well. And that's really the gist of it for all these different options here. It's really a balance, because if you change a number in one way or another, you're going to see different results. So you got to really strike a balance. Okay, so I reset our batch size back to 512, and now we see our familiar curve that we have here. Let's go ahead and change another thing here. Let's just try changing the number of neurons that we have in our first hidden layer. Let's change it from 16 to 32, and let's see how that affects the performance of our model. While this is going, the number of neurons usually makes it so that the dimensionality of the network is larger, so it has more capability to learn more complex patterns. There's usually a correlation between the complexity of your model and overfitting. So a more complex model, like I said, will have the tendency to overfit more, and then a more simple model could help dampen overfitting. Okay, just like I said, you gotta strike a balance, right? So anyways, let's go down here, let's see what we got. So this is our current results. Now let's go ahead and run this. And okay, so we give something very similar. It doesn't really change very much, which is actually pretty good. Let's change it to a much larger value. Like we can do 64 neurons, and we'll leave the second one. We'll change the second one to 32. Okay, let's just see what that looks like as well. And look at that. So now we can see a little bit what we saw before when we had a smaller batch size. We can see that it starts to overfit right away, which kind of lines up with what I just explained. The more complex your model is, the more complex patterns it can start to learn. But for this particular example, the more complex our model is, the more it starts to overfit right away. So it immediately converges. It's still at just under 0.3, which is good, but you can see that it right away starts to reach that optimal point of validation loss and then start to overfit from there. So now that we have this model, it's not very useful if we can't make predictions with it. That's why we made the model in the first place. So to make predictions, we can do predictions is equal to model.predict. And now we just want to give it input that we want to actually calculate predictions for. So something easy that you could do is just pass in the test set. Boom, there we go. Now we have predictions. And let's just go ahead and print out what those predictions look like. Let's see what it gave us. Looks like we have a NumPy array. It's a matrix filled with float 32 values. So let's just access the first one. And so we can see that the value of the first one is 0.07. We can print it out by doing that. So we get 0.07236.935. So we can see that this is a very small number. And if we compare it to the actual label for this, so we could do y-test 0, it should be 0, right? So the reason that it's not a 0 or 1 is because, again, the output layer that we specified for our neural network, it uses the activation of sigmoid, which will squash our values in our network to the range of 0 to 1 inclusive. And again, this represents the probability of the target being 1 or positive. So that is why it's not 0 or 1, it's a probability. The probability that is the positive case of 1 or positive sentiment. So the way that it works pretty much is that there's a threshold. And so if it's under 0.5 in terms of the probability output, then it's going to be labeled 0. And then if it's 0.5 or above, then it's going to be 1. So in this case, this is far below 0.5, so it's going to be interpreted as a 0, which matches our actual label. If we were to change this to the second one, now we get 0.99, which is very high, almost 1. And compared to the actual label, we get 1. So we can see that the model really thinks that this prediction here should be labeled as 1 or positive sentiment, and that lines up correctly with our actual label that it should be. So that is how you can make predictions, and that's how they work in terms of representing probabilities. And then our loss function, which we specified before, which is our binary cross entropy loss, this internally uses that threshold to determine which label is going to be used based on that probability. Okay, so hopefully that is interesting. Anyways, that's all I want to show for this part here. Now you guys know how to do the IMDB binary classification. In the next part, we're going to do another example of classification, so stay tuned. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.